is what I mean. All right. Go back to it then. So I resumed the recording. Sorry about that. It seems like there's a bit of confusion a while ago with the slides. All right, so let's look at the linear regulator here, right? So I think I had mentioned this before. That's why I thought it was the wrong slides I have here. All right, so just to repeat this, if you consider this circuit that we have here, the input voltage, as this is a DC input, and we're using a transistor here as our switch, and we have our load. If we just apply Kirchhoff's voltage law around this loop, right? So we would have what, V in, and then the voltage drop across the transistor, right, plus VCE plus the voltage drop across, sorry, let me take that out. Voltage drop across VCE plus the voltage drop across the load, that's V out, and then minus V in, and that's equal to 0. So rearranging this, making the output voltage the subject of the formula, you can see where we get that V out is equal to V in minus the voltage drop between the common and the emitter. All right, so if we replace this switch, this transistor that we're using here as a switch, by just a variable resistor as shown here, then it can achieve the same job, right? The same result here. Now, what would be the main difference between this and this, right? Because we're using a resistor here, it is going to be not as efficient as with this kind of switching using our transistor, right? So this with the resistor will consume more electricity, right, and reduce our overall efficiency of the circuit. So you have more power loss, right, using this way, right? So when we, right, I'm just showing you here, when you do the calculation, you can see that you have a higher power loss when we use the resistor there as shown. All right, so when we use the transistor in this format, right, we provide a pulse to switch it on and off, right? So we're moving from this way, just having it going in the operating in the linear active mode. We're going to apply a pulse at the gate of this transistor. So it's switching it on. So here is just an equivalent circuit here showing you. And to switch it on and off, right? So what you're getting, it comes on, then it goes off, comes on, then goes off, right? By this method, you will realize that you will have very little power loss, right? Very little power loss will be realized here. Right? Most of the power from the source will be transferred directly to the load, right? With this kind of switching. And of course, I think I should go back over this. I know some people probably don't remember how we get this in this region where we have the off, be the duty cycle multiplied by the time here. So let me go back over this part since let me keep, let me just get a little page here. Right here. Put a page here. All right, so I just want to make this part clear. I think I've done it already, but when we say duty cycle, let's consider this pulse. All right, so by definition, when we say duty cycle, it's the on time, let's say T on to the period T. That's what we mean by a duty cycle. So here, the period for this would be from here to here. So that's your period T. All right, now, so T on, right? So this is T on in here. And we have T off right here. Right, so your T is just equal to T on plus T off, right? That's your period, right? So there's just summation of the time that is on and the time that it's off. Now, the time that it's on, T on, we can write this as the duty cycle multiplied by T. So you'll see for in this region, we'll have can write D times T for the duty cycle, or the time that is on. However, in the section we'll have T off in this portion of the waveform for T off. Okay, if we know that from this point up to this point in the wave, in the signal, it's T, then how do we find this part, T off, right? So T off, that will just be minus your duty cycle times time, that's T on, right? Right, we just rearrange this one, right? This expression, right? T equal T on plus T off, right? What is T off? T minus T on, right? And T on is equal to the D times T, right? So I can factor out my T, and that's 1 minus D. So in this region, where we have T off, I can write it as 1 plus T into 1 minus D. All right, I'll be using this a lot. Make sure I review it. All right, so let's go back to this. Now, you can see here when the switch is closed, right? That's on, and it's off. We have our this is the 1 minus right here is 1 minus D right in this region, right? So basically we have 100% of our power going to our load with this type of switching, right? So all of it goes to our load with this type, and this is a heart. What I've shown you here is a heart of all the converters that I'll be going through with you now, and this is how it is explained in terms of the efficiency, right? So as I say, the switching regulator is the basis of all DC-DC converters. So the first converter, right? I'll just go through that before we wrap up. All right, so what we are looking at here, the buck, right? The buck converter, or what we call a step-down converter. In a little while, I hope I'll be able to explain to you why we say step-down converter. All right, so VD, that's the input to your converter. You have your switch here, and this switch, it could be any of those power switches that we studied earlier on. It could be your IGBT, it could be a power MOSFET, it could be a BJT, right? So you have your diode, you have your inductor, your capacitor, and you have your resistor here, right? So, and this is the basic, what we call topology, right? So if you're asked to draw the basic topology of your buck or your step-down converter, this is what it looks like. And as I've shown you here, it's all this switch is controlled by some pulse mechanism, right? So as I've shown you earlier on, the switch is controlled by some pulse so that it can turn this switch on and off. So let's analyze the buck converter. Right, in analyzing it, we're going to look at two states: when the switch is on and when the switch is off. Switch on, it closes; switch off, it is open. Right, so what is happening? In the first instance, when we have the switch closing, our diode is basically out of the circuit, right? If you look at this, switch closes, right? So it's reverse bias. No current will flow in this direction, right? So it's as if it's out of the circuit. So I'll draw here open circuit for it, and we have a current now that will flow through our inductor, right? But what is the voltage? Can you tell me the voltage that will be dropped across this inductor? What's the voltage that will be dropped across this inductor? All right, so you know that you have VD here, but what's the voltage that will be dropped at this point? All right, so let me help you. Pardon me? Right, so we know by looking at this diagram, the voltage here would be VD, right? What's the voltage here? The capacitor and this and the load, they are in parallel, so the same voltage. So the voltage drop here is V out. Right, so therefore, the voltage drop across the inductor when the switch is closed is just the difference, right? Potential difference, right? So that would just be the V out minus VD, right? Are you following? Potential, sorry, VD minus V out. Sorry, VD minus V out. So that's the um, the difference in potential that we have here. And similarly, we can do the same reasoning for when the switch is open, right? Switch is open, right? What is happening? Switch opens. It's as if the supply is out of the circuit. Supply is out of the circuit, and what you'll have happening now, the inductor would have stored some energy. Also, the capacitor would have been charged. So what you have, energy will now be released in this circuit, right? So the diode would now be closed, right? So the diode is now forward biased. So what's the voltage across the inductor? What's the voltage at this point? What's the voltage here? Right? It's clearly zero, right? It's clearly zero. You can consider this being at Earth down here, Earth. Right, so this is zero right here, and the voltage right here would be V out. So across the inductor, the voltage drop when the switch is closed would be 0 minus V out. Right, so that's basically just minus V out. Minus V out. This is all from your networks that we're doing. So we can analyze this. Hopefully what I'm doing here will be clear to you. All right, so we're going to do the same thing, right? So this is our circuit. We're going to consider it when it is closed. All right, so I have it closed here, right? So of course, at that point is as if the diode is with reverse bias, as I explained earlier on, and we can work out the voltage drop across the inductor, so where it's just equal to the input voltage, right? That's VD, input voltage, minus the output voltage that we have here. Right? So VD minus V out. When we look at the graph, we start at this point. So here we have VD minus V out. Right? So this is a region when the switch is closed here, right? So we can now set this equal to LDI dt. Why can we do that? We know that the voltage drop across the inductor is just given by LDI dt, so we can set it equal to it, right? So let's work out the current, right? Because that current would now be equal to 1 over L in the integral of VL. This is very simple. You just rearrange the expression, right? Making current the subject of the formula. It is in your DIDL, right? So you're just rearranging this expression right here. Let me just get a little space up here, right? So this would be VL over L, right? just moving across, right? So VL over L, and this would be dt on one side, and this equal to di on the other side, di dl. So you integrate both sides, right? Both sides of this expression, right? So this side, you're going to integrate. This side, you're going to integrate, right? And of course, with respect to t, and that's how we have our I being equal to 1 over L integral of the voltage across our inductor. Right, so we can see clearly that the current during this time when the switch is closed is increasing. Because you look at this current and time, right? The current and time, there's a proportional relationship here. So that is why we have the current increasing in this region, right? So again, what we have seen is that we have some voltage across the inductor that is given by Vd minus Vout, as seen on the graph. And at the same time, we work out by using the expression here. We see that the current that will be flowing through the inductor would just be increasing, right? So it increases. That's what we are showing in this region when the switch is closed. All right, so we next turn our attention to analyzing it when the switch is open. And of course, we would have worked out already. So I won't have to go into that again. Right, so the voltage up across our inductor at that point would be minus V out. Right, so here the voltage here is 0, and at this point V out, so the difference in voltage, right, is minus, right? So here 0, and here V out, so difference is equal to minus V out. I forgot to mention that this diode here is acting as a freewheeling diode, right? Now, on the graph, let's now analyze that. The first part, we have analyzed it already. We know how we get this line going up when we look at a graph of current versus time. We have the current going from some minimum, it rises up to some maximum value. And we have, when it is closed, we have V, the difference between the input and the output voltage, right? So when it is open, it's minus V out, right? So open comes down to minus V out, as you are seeing in this graph. And of course, during that time, all right, remember it's now off. So that's how I have here 1 minus the duty cycle multiplied by the period. Right, so that's how I get this part. And you will recall that when it is open, when it's closed, it's just the duty cycle times time. But for off, it is 1 minus the duty cycle times the time. And if you set this to do the math again, you're going to see, let me just explain to you how we get that current, right? So you substitute again in that expression for the voltage across the inductor, and you see now because of the minus, you'll have the current going in the opposite direction. All right, now when the switch is closed, right, we're now going to just set that voltage. You know that in that region here, when it's closed, voltage up across the inductor is just Vd minus the input voltage minus the output voltage. And we know that that's equal to inductor inductance multiplied by the change in current with time. All right, so here you can just rearrange this expression, right? Make di dt, change in current with respect to time, the subject of the formula, and we just have this expression here, right? Input voltage minus output divided by our inductance. All right, now what do we mean by di dt? It's just a change in current, so delta I over delta t. All right, now your delta t, what is delta t? Right, I've shown you earlier on that when the switch is closed, that delta t is just equal to duty cycle times time. So that's what I have here. Of course, we set this equal to this, right? So the input, remember, is equal to this expression here. So write it back. And we're going to now make delta I the subject of the formula, and that gives us the current that is flowing when it is closed. So I just rearrange this to make delta I the subject of the formula. So this goes up, and that's how I get this part. We're now going to do the same thing when the switch is open, right? So remember that the voltage up across the inductor is just minus V out, and that's, of course, that's equal to LVI dt. And of course, you're changing current with respect to time. Just rearrange this expression and making di dt subject of the formula. That's just minus V out over L. Of course, same kind of analysis. What do we mean by di dt, change in current over change in time? Recall when we have the change in time from when it is open, it's just equal to 1 minus d multiplied by t. That's the duty, 1 minus duty cycle multiplied by the period. Of course, it's equal to minus V out over L. So we're going to find the change in current when the switch is open. So just rearrange this expression, right? So we have minus V out over L. Just bring this up, that's all. Bring this up, the 1 minus d times t, bring that up, and we get this expression. But now, when delta I when it's open must be equal to delta I when it is closed, right? For continuity, right? So you can look at what will happen. So at steady state, right, we want the delta I, the change in current when it's closed plus the change in current when it's open, to be equal to 0, right? That's what happens at steady state, right? Otherwise, what we can have is an unstable state, right? Would be unstable current where you observe it ramping up or it's decaying, right? So what we will look at is in steady state. That's what is desirous. So at steady state, you can write this expression, right? Changing current when it's closed plus changing current when it is open, that's equal to 0. And we substitute the 2. And this is what it is. When we simplify it, we have that the output voltage is equal to duty cycle multiplied by the input voltage. And this is your equation that defines your buck converter. Right? So clearly what you're seeing here is that the output voltage is going to be some fraction of the duty cycle, right? So output voltage is going to be less than the input voltage. Hence, we say a buck converter. All right, I think we can stop here for today. I think I've gone over. Um, so here's